Okay, so Alex, if you want to turn on your camera.
Hello.
There you are. So let me introduce him. Alex Candello is the Director of Algorithms, Performance, and Tools at D-Wave. His responsibilities include the Ocean Quantum Software Development Kit, D-Wave suite of quantum tools, benchmarking, the development of hybrid algorithms that combine classical and quantum resources, one of which you'll see today, and professional services. Alex earned a Master's of Applied Science and Mathematics from Queen's University in Canada. So go ahead.
Oh, awesome. Thanks, Susan. Hey, everyone. Excited to be here today. As Susan said, my name's Alex, and I'm the Director of Algorithms, Performance, and Tools here at D-Wave Systems. I'm really excited to be here to show you a demo of our constrained quadratic model hybrid solver and some of the new features of that solver that we launched a few weeks ago, earlier this month, or last month. I suppose it's June 1st now. Okay, so before we jump into the demo, I want to talk a little bit about how we think about solving problems with a quantum computer at a commercial scale. Because quantum computers are fairly opinionated. They're, we have 5,000 qubits, but it's actually not all that large in the grand scheme of things. They're very specific, and you might need a lot of knowledge about how to use that most effectively. And so in order to meet that, to take that and use it at a commercial scale, which is very large and very abstract and very, hand wavy, like, oh, I need better scheduling. You actually need quite a deep stack in order to have those two things meet in the middle. So to kind of walk through like what a comprehensive full commercial stack looks like for quantum computing, I want to actually just sort of walk through the various aspects of this slide. So at one end of the spectrum, on the sort of far left, you need a quantum computer. I mean, you need a quantum computer in order to do quantum computing. That seems fairly self-evident. And the quantum computer of choice for us is the Advantage processor, which is our 5,000 qubit processor that we use available in Leap right now. In fact, you could go sign up for Leap right now and get access to it. This is our sort of commercial grade quantum annealing platform that we use to solve problems. But just a quantum computer by itself isn't all that useful. You actually need to be able to access it. You need cloud access, you need scheduling, you need authentication, you need quota management, you need hybrid solvers, which I'm going to be talking about quite a bit later. And all of those are available in Leap, our cloud platform that, again, you could sign up for right now. Okay, great. You got a quantum computer, you got some hybrid solvers, you got quota management, you got a scheduler. It's all hanging out in the cloud ready to go. But you're going to need to be able to put your problem onto it. You're going to need to be able to specify your problem in such a way that it can be submitted. And for that, we have Ocean, our set of open source tools. And then finally, for some folks, that's enough. That's all they need. But for other folks, maybe they're looking for a little bit of help, or they're looking to do something new or unusual or that has never been done before. And for that, you need professional services, which is our launch program. And we do a 4-phase engagement model where we walk through the process of identifying a good problem, mapping that problem to the system, testing its performance, and then hopefully, ideally, at the end, going into production. So today, I want to hone in on a specific aspect of that journey. Specifically, I want to be focusing in on the hybrid solvers. So a hybrid solver is at once very complicated and very simple. The simple form of it, the short version, is that it is a solver that combines the best of both quantum and classical resources together so that you get the full benefit of both. The basic idea is this. As I said, quantum computers are opinionated. They're relatively low level. It'd be like writing machine code for a CPU to be programming that directly. A hybrid solver abstracts all of that away. It brings all of our best knowledge here at D-Wave of how to solve problems on quantum computers, how to solve problems using both together. And it gives you both the robustness of having both classical and quantum resources, as well as the scale that really is needed to solve practical problems. And finally, it allows you to abstract that so that you can specify your problem, hopefully in a way that's sort of natural and native to you, and not necessarily the way that is natural and native to the quantum computer, which those two things are not necessarily the same thing. So the particular hybrid solver that I want to be focusing in on today is our so-called constrained quadratic model solver. Specifically, we're interested in its new feature, which is continuous variables. So I'm going to be going through a lot of those words and aspects in a little bit more detail later, but I'll just run through it really quickly, which is that our constrained quadratic model solver is our, in some sense, most general solver. It allows you to specify problems over several variable types. So our quantum computer natively works in so-called spin variables. That is to say, variables that are either -1 or 1. But our hybrid solver, our continuous, or our CQM solver rather, allows you to solve problems with spin or binary or integer variables, or starting a few weeks ago, real or continuous variables. And that's been really important, and that's what I'm going to really be focusing on later. As the name might suggest, the other thing that the constrained quadratic model solver does is allow you to solve problems with constraints. Now, constraints are really important. They show up all the time. Every practical business problem I have ever run into has involved constraints. And constraints are things like, my set of delivery drivers can't work more than 8 hours, or my truck has a finite amount of fuel and it might run out. Or maybe I only have 7 trucks and I need one of them on call at any given time. All of these things are constraints. There's also other types of constraints that are important for formulating these sorts of problems. And those are just sort of like existence constraints, like a truck can't be in 2 places at the same time. That sort of thing is also important when you're trying to represent these problems, these sort of business problems mathematically. Okay, so hopefully that's enough of the sort of slideware. Let's jump into the fun part, which is the demo. So I'm going to stop sharing my screen really quick and jump over to. So I like to start the demos that I do here on our Leap dashboard. So if you were to sign up for Leap, and maybe some of you already have, and got a free Leap account, you would land in Leap right here. And I actually want to mention and emphasize that everything I'm doing today is available in Leap in real time in open source. You could literally click along one for everything that I'm doing and run it yourself and experiment with it and play with it. So this is all available in open source right now. Leap has a lot of really cool stuff. You can see problems that you've submitted. You can see the solvers you have access to. You can check out our interactive demos. You can access a whole pile of different resources. We have a community, all sorts of different really important and cool things in Leap. But today, I want to focus in on our set of open source examples. This set of examples are a collection of open source examples solving different problems using our quantum computer or our hybrid solvers. Most of these are industrially motivated. They're submitted either by customers or folks out there solving problems, or maybe they're a case study that we did based on a paper or something like that. Some of them are also fun. So you'll see like we have Sudoku solving and the like as well. Really, this is meant to be an opportunity to jumpstart your application. So you could find something that's close to what you want to solve and use that as a starting point for your sort of journey towards solving problems with our hybrid solvers or quantum computer. I'm going to be focusing in on a specific one, though, called 3D bin packing, and that's going to be the subject of our demo today. I'm actually going to go ahead and open that up in our online integrated developer environment in the background, just so that I can get started while I'm talking. But let's go ahead, before we jump over there, let's talk a little bit about this problem. So 3D bin packing is a fairly intuitive problem. The basic idea is this. I have a collection of different cases of different sizes, possibly shapes, possibly weights, and I want to pack them as efficiently as possible into a 3D space, a bin. This problem shows up all over the place in practical applications. This shows up in the context of, let's say I have a set of medical equipment that I want to ship. How many shipping containers might I need? Or maybe it shows up in I'm trying to figure out what's the right shape of box that I want to use that packs most efficiently into a, oops, the demo's excited to start, that fits most efficiently into a truck. Or maybe I'm interested in what size truck I want to use, or how many trucks I might need in order to do those demos. All of these different things are based on this basic problem of 3D bin packing. And I just want to emphasize now that over the course of this demo, we've made a lot of fairly arbitrary choices, in terms of like what size of boxes we want to use or what shape they are. But all of those things are configurable and, with relatively small amounts of work. So really, this is a really general problem that I'm just showing a specific instance of. And in fact, this demo is derived from work we did with Johnson & Johnson. This is an offshoot of a project that we worked with them, on a real practical industrial problem. So scrolling down, I want to give you a little bit of an idea of what makes this problem difficult. So in addition to, I think anybody who's packed a moving truck or something like that has run into this, but this is actually a really complicated problem with a really large solution space. Each of these boxes can be oriented in one of 6 different ways, and that's just assuming you have square boxes. If you have more complicated shapes, it can be even more. You have to place them in 3D space. You have to decide, how they're stacked on top of each other. You have to try to minimize the total height. The actual space of solutions to this problem is, it's infinite because you have continuous variables, but this is a really difficult solution space for a classical solver. In terms of the way that we think about solving these sorts of problems, we think about them in a couple terms. And the first thing that you need are your set of variables. Those variables are the thing that the hybrid solver is attempting to solve for. Those are the things that you're trying to optimize. And in this example, we have 2 types of variables. We have binary variables, which are yes or no, 0 or 1. Or in this case, is this box in that bin? Or is it in this other bin? That's a question that has a yes/no answer. We also have continuous variables, and those are ones that are anywhere on a spectrum between 0 and 1, or negative infinity to infinity, or 0.14675, or pi, or any of those numbers are continuous variables. And in this case, we use the continuous variables to define where in the bin our cases are. So am I 1 foot from the wall? Am I pi feet from the wall? Where am I in 3D space? Should I move it over? Just nudge it over a little bit to the left to create a little bit more room. We also use a continuous variable to specify the height of the overall boxes. So we want to keep those boxes as low to the ground as possible. And so we use a continuous variable to specify that height. Finally, the next thing we have is an objective over those variables. And in this case, our objective is to minimize the number of bins that we need. We also want to minimize the height of the boxes within that bin so that they're sitting on the ground. And finally, we want to minimize the total height across all of the boxes so that maybe we could pack more things on top later. And finally, as I mentioned earlier,
someone asked if you could zoom the screen a bit.
Oh, sure, I absolutely can.
It's kind of hard to read. Thank you.
Yep, thank you. The other thing that we need is a set of constraints. So our constraints are, in this case, things like 1 box can't be in more than 1 bin, or each case has exactly 1 orientation. They might also have other constraints, like maybe heavier boxes need to be below lighter boxes, things like that. So all of these different rules can be encoded with constraints. Okay, enough math and enough static images. Let's jump into the demo. So as I said, this is actually running out of our online integrated developer environment. This is it. We're only going to spend 1 moment on it just so I can tell you that it's here, because we're actually going to jump into the visual component of the demo, which, as I said, is just running out of this online developer environment. So for this example, let's just run a relatively small example just to get us sort of oriented. So the first thing I'm going to do is I'm actually going to set a seed so that we're running the same problem each time, and so we can do sort of repeated runs with the same problem. I'm also going to run this for about 8 seconds rather than 20 because I'm doing an online demo. For now, I want to pack 15 cases into 1 bin, and my cases are going to be between 1 and 5 feet in each dimension. I'm also going to pack them into a shipping container, which is about 20 feet long and about 9 feet tall, and about 8 feet wide and 8 feet high. Sorry about that, not 9.
Sorry, is it possible to zoom this screen as well?
Yep.
Thank you.
Okay, so let's go ahead and give this a run. So when I click run, what's going to happen is we're actually going to go through that journey that I had on that earlier slide, where it's going to, some smart professional services folks put together this problem as part of the launch program. Right now, it is constructing that problem using Ocean, our set of open source tools. It's submitting the problem to Leap, our cloud platform, and then our hybrid solver in Leap is making use of the quantum computer. And all of that just happened in real time, live in front of us. And when I take a look at the resulting problem, this is what it looks like. So it does look like, in fact, our hybrid solver was able to stack our 15 cases into 1 bin. So, hey, pretty cool. We can see that there was a sort of maximum minimum height because some of the cases were this size. And so it's, everything has been kept below that height. So, it's always nice in an online demo where everything works the way that you expect. So I want to contrast this now by running this exact same problem on a classical solver using just exactly the same problem that I was before. The classical solver that we're using in this case is CoinOr's branch and cut solver. This is an open source solver that solves the same basic problem class that we do. It's open source, which is why we're using it, but it is a good one. It's used in Google's operations research tools, as well as many other places. It's very popular. This is a good classical solver for this problem class. And taking a look, lo and behold, it has also solved the problem. Although actually, you can see right away, we actually have a little bit of a problem, which is that in the 8-second time limit, it wasn't able to find a solution that put all the boxes on the ground. We have one box there that's kind of hovering off the ground. So even at this relatively small scale, we're starting to see some struggles. But just to make this a little bit more interesting, let's make this a little bit harder. So 15 cases, as you can see, fits pretty comfortably onto the floor. You don't really need to do a lot of stacking. But let's just add 2 more cases to this problem. So we're just taking it from 15 to 17, which is really starting to add a stacking component. You're really starting to need to put several cases on top of each other in order to satisfy the constraints, or in order to place them in the box. And when we do that, we see that within that 8-second time limit, the wheels are really starting to come off here. Even just going from 15 cases to 17, we start seeing pretty poor performance on this problem. Lots of boxes hanging in the air, not really sort of the result that we want to see. So by the way that I've put together the demo, you can imagine what's coming next, which is that we're going to take that exact same problem for the exact same amount of time, and we're going to run it on one of our hybrid solvers available in the cloud. So, same boxes, same orientation, same problem specification, all that good stuff. And when we do that, we see right here that the hybrid CQM solver was able to get a lot further in that same amount of time in solving this problem. So it was able to do a better job of placing the boxes in that fixed time limit. And I think this really emphasizes something that we consider really important here at D-Wave, is that most customer problems, you want the best possible solution that you can get within a fixed time. That's really most often the way that folks come to us. It's not, we need a perfect solution. It's not, oh, take as long as you want. It's, I have to dispatch some trucks. Can you fill my shipping containers as quick? What's the best you can do within the amount of time that you have? So I want to just do one more, sort of make this harder one more time, which is that I want to take this from one case into one bin rather, into 2 bins. So I'm going to take the number of cases from 17 up to 30, which probably don't fit within the 2 bins. And I want to run that one more time on our constrained quadratic model solver, again, running within that 8-second time limit. I'm also going to mention that when you go from one case to 2, you get something called a quadratic interaction between the variables in the problem. Now, what a quadratic interaction is exactly is something that I'll defer to our sort of online docs and stuff to go into more detail, but intuitively, it's an interaction between the variables in the problem. So specifically, there's an interaction between the variable that says which bin each of the cases is in, and the variable that says how many bins there are. And so that sort of and you can see that we actually got these 522 quadratic interactions that appeared in this problem. But actually looking at this, it looks like I didn't make this problem hard enough. Actually, the hybrid solver rather was able to find a solution that put them all into one bin. So, I should have added more cases. Oh, well, that's cool. But let's take this same problem and finish this off by trying to solve this same problem on the classical solver. And when I do this, what I'm going to see is that we actually have a problem, which is that the classical solver isn't actually able to solve this problem at all. And that's because this particular classical solver only solves linear programs, i.e. not quadratic. They can't handle problems at all that have those quadratic interactions that I was describing before. And it's worth mentioning that these quadratic interactions are really where these problems become hard. And it is the native problem class of our quantum computer to solve quadratic problems. So this is really an area that we at D-Wave really are interested in and we like to solve problems in, because that's really sort of our bread and butter. So I'm going to jump right back. I'm going to jump back into the slides for just a few more. So just give me 1 second. So just to sort of summarize everything that you saw, let me move that over. We are now able to solve constrained problems at an industrial scale using continuous variables, which is, as far as I know, is an industry first for the quantum computing industry. We have been able to use this in the context of demonstrating business value. As I said, that example was derived from work with Johnson & Johnson. Our solvers provide convenience and time saving for customers. So our ability to specify these continuous variables, as well as the constrained quadratic models more generally, allow users to specify their problems in a language that is relatively easy to understand, and they get back solutions in good quality solutions in a small amount of time. I mean, finally, this ability to solve these constrained quadratic models and the continuous variables specifically have really opened up D-Wave's ability to solve a wide variety of problems in a lot of different industries. You know, I started at D-Wave actually in professional services. And when I was doing that, often I would get asked a question, which is, what sorts of problems are bad for quantum computing? And up until a few weeks ago, my answer would have been problems with continuous variables. But now that barrier has been removed, and all of a sudden we're able to solve even more problems than we were before. So I will leave the presentation part of it with a few different ways that you can get started with making use of our hybrid solvers or quantum computers. You can contact sales directly. You can check out our launch program, which is that sort of 4-step professional services program. You can check out a bunch of our different applications. You can do an ROI calculator. We have tons of online resources, and I would encourage you all to sign up for a free account for Leap if you haven't already. And with that, I will take some questions.
Great. Thanks, Alex. So again, if you have questions, please put them into the Q&A box. We've answered some of them during the talk, but we will ask and put Alex on the spot now. Is it possible to add soft constraints to a CQM by manually adjusting the penalty?
That's an awesome question. So right now, soft constraints, the CQM treats all of its constraints, like the things that you specify as constraints, as hard constraints. But you can add soft constraints to the objective just the way that you would before. So for anybody who's not 100% sure, the context, the idea is that you can specify in your objective that I would like to satisfy this constraint with a certain penalty. And so that's the way that you can do soft constraints right now.
Okay. The new floating point feature of the SDK, is it just an API extension convenience for adding variables to a model, i.e. simplifying model continuous variables, or are there some changes in the way the hybrid solver works with these variables, i.e. with their binary discretization or whatever representation is chosen for them?
Yeah, so it's both. So it's both a convenience function in the sense that it is more convenient to be able to specify problems this way. But we did change the hybrid solver under the hood to handle these continuous variables. And the way we did that is definitely the secret sauce of the hybrid solver. So it's pretty cool, but unfortunately, I can't really talk too much about it.
Okay. So converting quadratic terms into linear will solve it on the classical solver, or will it still remain big?
You definitely could convert. There are lots of tricks to converting quadratic interactions into linear ones. It's worth mentioning that not all of them work all the time. And they do create a bunch more auxiliary variables that start to appear or other issues. I haven't actually done that test in this case, so I'd be curious to know what the result is. I suspect that it would be pretty poor for the classical solver in this case. Okay.
For 30-bin problem, have you encoded every variable with 25 approximate qubits?
The relationship between the variables in the problem and the qubits that are used in the quantum computer ultimately it's complex. So the short answer is no. We use the quantum computer in the context of the overall hybrid solve, but it's not like there's like a really direct one-to-one relationship in that way.
Okay. Are you planning to support continuous variables and quadratic interactions of CQM solver soon?
Can't comment on timelines. It'll definitely depend on what customers are interested in. So I would really encourage you to make a feature request, open up an issue on our community or on one of our Ocean open source tools, or let the sales team know that that's of interest to your application. And we would prioritize our next releases accordingly.
Okay. How does the use of continuous variables affect the size of the problem after minor embedding? In other words, can the current D-Wave hardware tackle problems with continuous variables that are just as large as those with binary or discrete variables?
Yeah, so I sort of touched on this earlier, but I will say that it is the way that the hybrid solver makes use of the quantum computer is complex. And you can think of the quantum computer in that context as sort of a co-processor, like a GPU or something like that. And so there isn't sort of that like really direct relationship between the two. I will say that the use of continuous variables does not make the quantum computer less able to solve it. It doesn't make it harder for the quantum computer in some, if that answers your question.
Okay, someone is asking for a few more examples of continuous variable problems in business.
Sure. One would be sort of, if they show up in portfolio optimization problems, really anything with a price. So, let's say I want to buy a certain set of stocks that are maximizing my total return. That's a continuous variable, subject to certain risk conditions, which might also be a continuous variable. Another example might be some of these sort of 3D space problems. So like you might be doing like protein folding, something like that, in which case you might want to represent the locations of the different atoms or molecules in 3D space. Other examples would be you use them in the context of like planning for like scheduling. You might imagine that an employee might have a different start time that can sort of have a sliding scale, or might have a different amount of time that they spend at each of the stations. There's also the stock cutting problem, which is one where it's like I have a big roll of metal, and I want to slice it as efficiently as possible to match a certain set of shapes that different applications need. I mean, really, there's many different applications that these continuous variables are useful for.
Okay, well, here's a question that came in via the chat, but I'll ask it anyway. How many different ways of packing have been configured? How many percent of the container space is used for the best case? Are there different ways of packing achieving exactly the same percentage of container space utilized?
Yeah, so I could probably unpack the code a little bit for this demo to find the specific answers to those questions, but of course it would be highly dependent on the way that you specified the problem. It is true that most of these solutions are not unique. So for instance, if I have a cube as a box, I can orient it many different ways and they're all equivalent in this case, although, it is possible to extend this problem class to have a notion of like, this direction must be up, imagine you're shipping, televisions or something like that. But yeah, it's definitely true that the solutions aren't necessarily unique.
Okay, let's see. I know our panelists are answering a few other questions here. I think there was one other, which was pretty similar. Okay, someone's answering it, but pretty similar to what was asked before. Are there classical quadratic optimization softwares that can solve the second problem?
Yes, there are. There definitely are. Most of them are not open source, and therefore we don't really have access to them. I'd be super curious for folks to go benchmark this problem. This is definitely a case right now where there's a lot of different solvers competing in the same sort of state-of-the-art problem class. So it's really going to come down to your application, which one is the best one. And a big part of the launch program is coming to that answer, which is in fact using a hybrid solver the best solver? And sometimes the answer is no, although we of course like it when the answer is yes, and we feel very confident in our solver and our approach.
Okay, well, I think we have run out of questions here. We've run out of time. We're intending to make these kind of short and sweet, so hopefully everyone has gotten some value out of it. Again, this is being recorded and will be on our YouTube channel the next day or so. And stay tuned for more of these. In addition to our monthly webinars, the next one, by the way, is June 16th. It's going to be a very interesting topic presented by Multiverse on quantum and crypto, basically trying to predict the evolution of cryptocurrency economic networks. And so you can go to our website and find where to register for that. So thank you all very much. Alex, thanks so much. And we look forward to seeing you all again.
Really appreciate it. Thanks, everyone.
Bye-bye.